This video is over the concept of work in physics, which work is just energy, but specifically energy that's transferred to or from an object by means of a force. And we'll give an example here in just a moment. For work, we can calculate it as the force applied to an object over a distance, or we can also say that d is displacement. And so work is an energy, so it's in joules. F is the force doing the work on the object in newtons, and d is the distance over which the force is applied in meters. And so with work, we have to keep in mind three rules. And, for this, I might just give an example here. Let's say we have some object. Sorry about that. Which has weight mg. Let's say it has a normal force. Let's say we are pushing it, Fp, and let's say it's on a surface, so there is some friction. And let's say that the object moves a distance of, I don't know, just some distance d. Okay. And this won't be what we always see, but this is just an example. We're taking some object, we're pushing it, there's friction. So each of these forces we'd have to analyze and figure out which ones are doing work and how much work are they doing. So when I'm pushing on an object, my force Fp is along the direction of the distance. So in F and D, and I use a lowercase d here, but you guys get the idea. If F and D are in the same direction, we use the positive form of that equation, which I just showed you. The work is equal to F times distance. And so we can calculate the work done by pushing. If I want to see the work done by the friction, we'll notice that friction is working in the opposite direction as the distance, which is the second rule here. If F and D are in opposite directions, then the work will be equal to negative F times D, negative FF times D in that case. And so in this case, the friction force would be doing negative work. And finally, we have the normal force and gravitational force. Both of those are in perpendicular. They are perpendicular with the distance d. So F and D are perpendicular. We say that both of these forces do zero work. And of course, this situation could change. This is just simply an example. This is one of the typical examples we would see. And before we do an example here, I'll just kind of illustrate what work is. Let's say you have a block and it is sliding on a frictionless surface, so we'll say the coefficient of kinetic friction is 0, and it has some speed v1. It could be 1, it could be 2. Just imagine it has some speed to it. And then the block is over here somewhere. It was moving. And for over a distance d, I apply a force to it, Fp, some constant force I apply to it. And what I'm doing is I'm putting work into the block. And that's going to add energy to the block. And in this case, we're adding kinetic energy to the block. So after I give it a good push for over a distance d, it will keep moving with some new velocity, some new speed, v2. And so we have done work on the block. We have added energy to it, which goes back to our definition. Work is energy transferred to or from an object by means of a force. If there was friction, for that case, that would be like taking energy out of the object. And of course, the best thing to do here is to do an example. So we have a 5 kilogram block initially at rest, and it's pushed by a force F1 is 14 newtons to the right over a distance of 22.5 meters. And there is friction. The coefficient of kinetic friction is mu sub k is 0.2. So briefly here, quickly here, I'll just draw a free body diagram. Again, not always the situation you would see, but one we see pretty often. And I'll just draw here. It starts from rest, but we push on it over a distance 22.5 meters. I'll just say this is distance, which is in the direction of my push force. So we have some questions. What is the work done by force 1? Question B, what is the work done by the normal force? Question C, what is the work done by the gravitational force? D, what is the work done by friction? And E, what is the total amount of work done? In other words, what is the net work done on the object? So for part A, we want to know the work done by force 1, this one here. We look at the direction of the force and the direction of the distance. If they go in the same direction, then we can just say, actually, let me erase those. We can just say work 1 is just positive force 1 times distance, which they give us 14. The distance is 22.5. And so grabbing a calculator, we can say this is 315 joules of work is done by the force F1. Question B, what is the work done by the normal force? So we look at the normal force, and we look at the direction of the distance, and we note that those are perpendicular to each other. And so we can just say the work done by the normal force is 0. Just going back to our rule, right? Question C, what is the work done by the gravitational force? Here is the gravitational force. Here is the distance. And so once again, they are perpendicular to each other. So the work done by gravity is equal to 0. I should note here, not always is the normal force going to do 0 work. Not always is the gravitational force going to do work. This is just an example. Okay, finally, the work done by friction. Friction goes in this direction, distance goes here. So since those are opposite directions, we would use the work done by friction is negative friction force times distance. We know distance. Of course, they don't give us the friction force here. They do give us mu sub k, and so we remember that the friction force is mu sub k times Fn, kinetic friction, that is. And so we continue. We don't know Fn, not exactly, but we do know that it is equal in this case to mg. By the way, it is not always equal to mg. And I do this in a different color so we can remember that there's a negative there. And so we have negative, mu sub k is 0.2. mg, what's the mass of this thing? So mg is together 50, and the distance is 22.5. There we go. Negative 225 joules. Okay, well, there's two more questions, F and G, some more questions there. We will get to those in just a bit. First, we need to figure out part E. What is the net work equal to? I'm going to do part E down here. The net work is another name for the total work done on the object, which includes the work done by F1, the work done by the normal force, the work done by gravitational force, and the work done by friction. And here we can note that we can write down that those are both 0. And so the net work is 315 minus 225 joules. As I'm pushing it, I am adding energy into the block, or adding energy to the block, and friction is doing negative work. It's kind of like taking energy away from the block. And what kind of energy is this? This really amounts to kinetic energy. But let's solve this. Let's say 315 minus 225. And so the total work done is a positive 90 joules. In other words, we have added 90 joules of energy to the block. So question F is, what is then the final kinetic energy of the block? And G is, what is the final speed of the block? But we should write this down first. So this is called the work kinetic energy theorem. It's an equation. And it says that the total work done on an object will equal the change in kinetic energy of the object. And the change in kinetic energy, we're going to write it as final kinetic energy minus the initial kinetic energy. And we're really going to use this form of the equation and occasionally maybe use that one. But we'll use the bottom one more often. So what this means is if I add a net amount of work to an object, then it will change its kinetic energy. In this particular case, we have added 90 joules of energy, and so, well, let's solve part F, which is what is the final kinetic energy. So we will use the work kinetic energy theorem. We know the net work is 90. We're trying to figure out what is the final kinetic energy of the block. And so we had to ask ourselves, what is Ki? What is the initial kinetic energy of the block? We could do a side calculation here. The initial kinetic energy is the mass times the initial speed squared over 2. But then we realize that the initial speed, since it was at rest, is 0. And so that is 0. 0 squared is 0 times mass is still just, this is all just 0. So we can cross it out here. It will not always be 0. And so this is simply our answer. So I'm going to write joules, kind of squeeze that in there. And so finally, G, what is the final speed? So we will say the final kinetic energy is equal to the mass times the final speed squared over 2. 90. The mass of the block is 5. And we'll just solve this for the final speed. And so the final speed of the block is 6 meters per second. So your equations that you should remember moving forward, the work kinetic energy theorem especially this one down here. And our work equation, remembering these three rules. And I think that is it. On some of your problems and your assignments, the initial speed of the object is not 0, and so you may have to calculate the initial kinetic energy as we would have done here, except that won't be 0, it'll be some other number.